OH-6, the highest performance light observation helicopter in the Army's inventory. You will soon be flying this LOH. Obviously, the OH-6 is a fast, powerful, responsive, and stable aircraft. Let's see what gives the aircraft these desirable qualities. The OH-6 is small. Its total length from the forward edge of the rotor disc to the trailing edge of the tail rotor disc is just over 30 feet. Its rotor diameter is slightly more than 26 feet. This compactness gives the OH-6 excellent close-quarters maneuverability. The aircraft has clean lines. The teardrop-shaped fuselage is the result of wind tunnel testing to provide minimum drag. Even the landing gear struts have fairings to reduce aerodynamic drag. The clean lines of the OH-6 are part of the reason for its speed and stability. Another contributing factor is the powerful, lightweight turbine power plant. The small turboshaft engine weighs only 136 pounds. Its military rating is 317 horsepower, but installed in the OH-6A, it is derated to just over 250 horsepower. This favorable horsepower-to-weight ratio adds greatly to the OH-6A's speed, power, responsiveness, and stability. The engine, like most of the aircraft's major components, can be quickly removed and replaced under field conditions. The engine's power is not wasted in carrying and operating a heavy and complex main and tail rotor drive system. The engine drives a total of only 4 gears in the main transmission, with 2 gear meshes. In the tail rotor gearbox, there are 2 gears and 1 gear mesh. The tail rotor drive shaft is one piece, lightweight and dynamically balanced. It has no supporting bearings and no universal joints. The simplicity of the drive system provides lightweight, low power loss, and a minimum of maintenance. The 4-bladed rotor system produces high lift with very little vertical vibration and rotor feedback. The blades are retained on the hub by laminated stainless steel straps. Each of the strap assemblies holds 2 opposing blades. These blade retaining straps have many unique advantages. The principal one is that they provide both flapping and feathering without the heavy joints and thrust bearings used in conventional rotor heads. Since much more force is imposed by flapping than by the centrifugal force of blade retention, broken straps will usually cause an out-of-track blade condition long before there is any possibility of blade loss. Thus, the blade retaining straps provide full articulation, freedom from joints and bearings, with minimum maintenance required. Each of the blades is a friction-type damper connected to the blade root through a damper arm and attaching pin. These dampers serve to restrain lead and lag motion and keep the blades an equal distance apart. No components of the rotor head requires lubrication, and on the OH6 there are only 3 sight gauges, one each to check lubricant level in the main rotor transmission, the engine, and the tail rotor transmission. Before each engine start, the blades and dampers must be rephased by pushing each of the blades forward in the direction of rotation, as the tail rotor is held firmly. This resets the dampers to their minimum friction setting and spaces the blades at equal intervals around the hub. This is also a good time to check the condition of the main rotor blades. The aircraft has been specifically designed to avoid the need for boost or automatic stabilization equipment. It consists of simple bell cranks. And push-pull tubes. No lubrication is required on any of the joints or bearings in the entire flight control system. On each cyclic control, there is a cyclic trim switch, which is used to electrically adjust longitudinal and lateral trim force. The cyclic system also contains a one-way lock, which resists aft stick movement. On each of the collective pitch sticks, there is an N2 governor trim switch. This switch permits the pilot to control N2 speed within governor range. With engine speed control, cyclic trim, and the cyclic one-way lock to resist rearward cyclic force, the OH6 is a very comfortable, stable aircraft to fly. The tail configuration also lends it stability. The stabilizers are almost as large as those found on small fixed-wing aircraft. At cruising speed, the horizontal stabilizer provides longitudinal stability. The vertical stabilizers contribute directional stability. The real proof of stability lies in flying the aircraft. Its stability permits hands-off flying in straight and level flight. Yet the OH6 is agile and handles very much like a well-designed fixed-wing aircraft. Next, let us look briefly at the construction of the fuselage. The primary structure of the OH6 is a strong central A-frame formed by the bulkheads fore and aft of the cargo compartment. The main transmission and rotormast are at the top of the A. Thus, the cargo, armament, or passenger load is carried directly beneath the main rotor. Because of this, weight and balance, or CG problems, are seldom critical. The landing gear struts are connected to the trusses through shock absorbers, which reduce landing shock. And transmit the landing gear load to the fore and aft trusses. Beneath the A-frame is a wide keel beam which extends the entire length of the fuselage. This further strengthens the primary structure. The flight compartment seats, as well as shoulder harnesses and seat belts, are attached directly to the primary structure. The engine is attached to the rear of the A-frame. Thus, all critical components, including the engine, transmission, and rotormast, seats and pilot are directly attached to the strong A-frame structure. In the event of a crash, the secondary structure is designed to crush and absorb high-impact loads. While the outer surface absorbs the impact. The passengers are protected within the A-frame, and the flight compartment is protected from collapse by the height of the A-frame and the forward extension of the keel beam. The aircraft has provision for mounting armament kits on the left side. The machine gun kit consists of a 6-barrel minigun with selective rates of fire. Ammunition is carried in a narrow box near the forward bulkhead. A mechanically linked gun sight is used for aiming the minigun. The weapon is operated by a trigger and a gun elevation switch on the pilot's or co-pilot's cyclic stick grips. The OH-6 cargo compartment has provision for 2 folding seats for passengers. Without a co-pilot, seats are available for 3 passengers. However, 2 additional passengers can be carried if the standard passenger seats are not used. With an armament kit installed, a total of 4 passengers can be carried. Though the OH-6 is intended primarily as an observation aircraft, it is capable of performing many utility missions to small units. The OH-6 requires a minimum of maintenance. All major mechanical units are field replaceable by unit mechanics. But to an aviator, of course, the key question is, how does it fly? We will start at the beginning with hovering flight. As with any turbine helicopter, takeoff to a hover is started with collective pitch full down and throttle full open. While watching the N2 tachometer, the N2 governor is adjusted to operating power turbine RPM. Cyclic control force is trimmed to neutral with a cyclic trim switch. As collective pitch is increased, you will discover that the OH-6 is different. There is practically no turbine lag. Response to increased power demand comes in less than 1 second. Hover at about 3 feet and fine trim the cyclic control force to neutral. Check the instruments for all readings in the green and check the flight controls for proper response. A professional helicopter pilot will always make these hovering checks, even though he knows the aircraft will check out, because he also knows that it's better to discover control binding or instrument redline at a 3-foot hover than during takeoff. In making hovering turns, there is one caution which should be observed in the OH-6. Turns should be made slowly, especially when turning the tail into the wind. If moved too quickly into the wind, the large horizontal stabilizer can produce considerable lift. If through misjudgment you feel the tail rising during a hovering or low airspeed turn, you will have to apply positive aft cyclic to regain a level attitude. Sideward and rearward hovering flight must always be performed with caution. Aviators and other aircraft and personnel on the ground have no warning of your intention to move sideward or rearward. Always make a clearing turn. In the OH-6, you will find that it is dangerously easy to develop too much speed in sideward or rearward flight. The reason for this is the exceptionally low drag of the fuselage. Proceed cautiously and very slowly until you are completely familiar with the aircraft's characteristics. In actual operation, Rearward flight is not good practice for moves of more than a few feet, but it is excellent as a practice maneuver to give you experience and confidence in maneuvering the aircraft. When you have gotten the feel of the aircraft and hovering maneuvers, you are ready for normal takeoff. Takeoff from a hover permits you to check controls and engine instruments, as well as to make a clearing turn. With a twist grip in the full open position, smoothly apply cyclic to start forward movement. And maintain your 3-foot altitude with collective pitch. Accelerate forward until you gain effective translational lift. As the aircraft starts to rise, attain an attitude which will provide an airspeed of 60 knots. Establish the desired rate of climb by adjusting power. Power requirement will, of course, depend on your load and density altitude. As a general rule, the OH-6 can make a normal takeoff under any conditions of load and density altitude where it is capable of hovering at 3 feet. Takeoff from a hover is the normal procedure. However, takeoff directly from the ground is an accepted form of normal takeoff. Since takeoff from the ground does not permit a clearing turn, it is essential to check thoroughly for other traffic. To initiate takeoff, center the cyclic and apply collective pitch to extend the struts. As the aircraft becomes light on its skids, gradually increase collective pitch. The OH-6 will start to accelerate forward. For a perfect takeoff, you must establish a rate of climb and acceleration which bring you to an altitude of 3 feet and into effective translational lift simultaneously. Takeoff power should be maintained until a safe auto-rotative airspeed and altitude is reached. As soon as a smooth rate of acceleration is achieved, stabilize airspeed and engine torque. We will not spend time on the standard flight maneuvers, straight and level flight, climbs, descents, level, climbing, and descending turns. Your skill in other aircraft can be readily applied to the OH-6. Cyclic trim should be adjusted for the desired cyclic stick cruise position. Trim is correct when small controlled displacements in any direction require approximately the same force. N2 may be trimmed within the green to provide the best comfort level. The OH-6 cruise speed is fast compared with other light helicopters. It can easily keep pace with larger, more powerful rotary wing aircraft. The OH-6 maneuvers easily and control pressures are light. Normal approach and landing in the OH-6 is made with a standard rotary wing technique. Entry altitude approximately 300 feet above terrain, airspeed 60 knots, N2 RPM in the green reading. When an approach angle of 8 to 10 degrees is intercepted, reduce collective pitch to establish and maintain your angle of approach. As you approach, you will reach a point where ground speed and rate of closure seem to increase. This is the point to start decreasing forward speed. Maintain forward speed at about the pace of a brisk walk until the aircraft begins to lose translational lift. At this point, reduce rate of closure and airspeed to stop both descent and forward movement over the intended landing spot. Because of the aircraft's low drag, you may find a tendency to float right past the intended spot. You'll learn to correct this with a little practice. After a few hours, you'll really learn to appreciate the fine qualities built into the OH-6. OH-6 is small and compact, giving it excellent close quarters maneuverability. Its teardrop fuselage and freedom from projection give it exceedingly low drag. Its 136-pound, 317-horsepower engine give it more than adequate power. Its simple powertrain is light in weight, with low power loss and minimum maintenance. Its flexible stainless steel blade retaining straps provide feathering and flapping without bearings or joints. It has only 3 sight gauges: transmission, engine, and tail rotor. It has no hydraulic system, and it has no grease fittings. It has a simple flight control system without boost or ASE. Its large stabilizers provide longitudinal and directional stability. It can be trimmed to fly hands-off. It is stable and agile, with quick and positive response to flight controls and throttle. Its fuselage is built around a sturdy A-frame and deep keel beam to which all major components are attached. It mounts a machine gun kit. It responds quickly and easily in hovering maneuvers. It must be hovered sideward and rearward cautiously. With its clean lines, excessive speed can easily be gained. Its takeoff requires no unusual procedure. And its approach and landing is equally simple. It is a small, powerful, highly maneuverable, and very useful aircraft. This is the type of work the OH-6 was designed for. Operation in the field with an ability to land and take off from very small and unprepared areas. Field operation is the principal subject of this film. But first, we must learn how the OH-6 is handled in 2 important maneuvers: maximum performance takeoff and steep approach. These maneuvers are 2 essentials of confined area operation. Every helicopter has somewhat different maximum performance takeoff characteristics and requirements. Power requirements in the OH-6 call for twist grip full open to to provide an N2 tack reading of 103%. During the climb, collective pitch must be skillfully manipulated to obtain the desired torque pressure. These are the basic requirements. We'll cover the fine points in a demonstration takeoff over an 80-foot barrier with the aircraft 50 feet from the barrier. With the cyclic in the neutral position, slowly increase RPM to obtain the desired N2 reading of 103% N2 RPM. When N2 is stabilized, check the rest of the panel. Then make sure that you are clear for takeoff. Be sure to check for aircraft overhead. Apply collective slowly and smoothly. Avoid any movement along the ground. Continue to apply pitch. As the 086 becomes light on the skids and leaves the ground, adjust the cyclic to a 40-knot airspeed attitude. A constant heading is required to attain smooth ascent. Pitch must be adjusted to maintain the desired torque pressure. In training, maximum performance takeoffs are terminated at about 100 feet. In the field, you terminate as soon as the barrier is cleared by increasing airspeed and adjusting power for a normal climb. As we watch a maximum performance takeoff, we can readily see that the maneuver differs from normal takeoff only in the fact that a gain in altitude is favored over a gain in airspeed. During the early phase of a max takeoff, before achieving 40 knots, you may not be able to make a safe auto-rotation in the event of engine failure. For this reason, maximum performance takeoff should be limited to absolute necessity. For the steep approach usually required in confined area operation, twist grip should be full open. Entry during practice is from traffic pattern altitude. Approach angle is 12 to 15 degrees. And entry airspeed is 60 knots. The angle of approach is the only difference between steep approach and normal approach. Both types of approach are made at an altitude of 300 feet or traffic altitude. And steep approach is initiated at an angle only 4 or 5 degrees greater than normal. With practice, you will learn to recognize the sight pictures for the OH-6. Each aviator will have a slightly different point of view depending on his height. The normal approach, 8 to 10 degrees sight picture, will look about like this. To reach the steep approach entry point, continue beyond the normal approach sight picture until your intended touchdown point looks about like this. To make this steeper descent, a greater reduction of collective pitch is normally required. Airspeed should be kept as closely to 60 knots as possible. A straight angle of descent is maintained by adjustment of collective. The helicopter may be crabbed to maintain a straight ground track above 50 feet. When you reach the point where ground speed and rate of closure seem to increase, adjust airspeed to the pace of a brisk walk. Maintain this rate of closure until translational lift starts to decrease. Apply power to compensate for loss of lift and gradually reduce forward speed to come to a halt on or above the intended touchdown point. Steep approach differs from normal approach only in angle of descent. The steeper angle of descent requires closer monitoring of rate of descent and rate of closure. You will need proficiency in these two maneuvers before you can undertake confined area operation. And in confined area operation, you must also be able to evaluate the area and plan every move you will make in getting into and out of it. Every forest clearing presents its own particular problems. Built-up areas present a completely different set of problems. Are there almost invisible wires or antenna masts? Is there an adequate avenue of approach and landing? Is there sufficient room to safely maneuver the aircraft into a good takeoff position? To answer these questions, you must be able to formulate a sound plan for landing, ground movement, and takeoff. To guide you in confined area operation, you can use a proven 5-step procedure. First, high reconnaissance to plan the entire landing, ground movement, and takeoff. Next, approach according to the plan established in high reconnaissance. Then low reconnaissance to make a final decision on the suitability of the landing area. Followed by ground reconnaissance to plan ground movement and takeoff. Finally, takeoff based on your plan. This confined area procedure should not be new to you. Its value has been proven through years of use. High reconnaissance is definitely the most important of the 5 steps. During high reconnaissance, you make the key decision. You will attempt to land or you will not attempt to land. Each high reconnaissance for a confined area landing is a test of your ability as a professional aviator, and each area will present you with a different problem. Let's examine this area. In a sketch, we can see its features more clearly. Most aviators would first examine the surface on which they intend to land. This surface seems to be ideal, good, level, firm sod, but it might be less ideal. It might have rocks and boulders strewn over its surface. Such obstructions would limit the usable area and make ground movement difficult. Or it might be wet and boggy, perhaps not firm enough to support your aircraft. A dry, sandy surface might cause a blowing dust problem, which would limit visibility on landing and takeoff. If the area had many shrubs or bushes, you'd have to be quite sure they weren't tall enough to interfere with your main or tail rotor. None of these surfaces make landing impossible, but they all must be evaluated carefully as you make your landing and takeoff plan. You'll seldom find a completely desirable area like this. There will almost always be a bad feature, like a large tree in the center of the area. Or a building with fences which obstruct part of the area. Buildings are a clue to another obstruction, wires. Overhead wires are difficult to see. Poles may be difficult to see, but they are your very best clue to wire. In the vicinity of buildings, even deserted structures, you'll frequently find wires. When you've decided that the landing area is clear enough, solid enough, and level enough to land on, you still have the question of how you will land and take off. In answering that question, you will have to take into consideration the wind direction, velocity, and consistency. If, for example, the wind was toward the tall trees at a velocity of 10 to 15 knots, you might consider an approach over the trees, even though they are the tallest barrier. Or you might consider an approach quartering into the wind to gain part of its advantage. But if there was only a 4 or 5 knot wind in this direction, you might consider a downwind approach to avoid the tall trees. Possibly you could use a crosswind approach, since the wind's velocity is not sufficient to be either a help or a hindrance. Wind direction and velocity are important factors, but wind consistency is perhaps more important. A wind blowing at a consistent or continual 10 knots can be a definite help or a definite hindrance, depending on its direction. But a wind which is inconsistent and constantly gusts over a wide range can be very dangerous. In a severe gusting situation, confined area landing and takeoff should be attempted with extreme caution. Suppose, for example, you are riding a 20-knot headwind on takeoff, but the wind drops to almost calm. With that additional lift gone, you might just make it over the barrier, or you might not. An inconsistent wind is worse than no wind at all, or even a mild tailwind in confined area work. One more wind factor which must be taken into account during high reconnaissance is a phenomenon called lee effect. Lee effect could be a problem in this landing area if the wind were in this direction over the tall trees. Out from the dense tree barrier is a wide area which is in the lee of the wind. In this area, the wind is masked or blocked. Although there may be a 20-knot wind above the trees, the wind at ground level is nearly calm. Making a normal to steep approach will be tricky. If the sudden drop in wind velocity is anticipated, it can be compensated for without difficulty. If it is not anticipated, the sudden loss of 20 knots of effective airspeed could cause falling through or loss of control. While tall trees can mask the wind, steep hills or tall buildings may have a considerably more noticeable lee effect. On the lee side of a hill, the effect can cause a marked downdraft, which is particularly dangerous in the initial phase of a takeoff or the final phase of landing. In high recon, you must consider wind, terrain, and barriers. You must plan your approach and takeoff paths. Takeoff should be visualized before landing. Final takeoff plans can wait until you're on the ground, but you must be sure you can take off. You must also consider your aircraft's gross weight. You must know the actual weight to properly evaluate the situation. In confined areas, the fuel load, equipment, and passengers must be kept within minimum safe limits. When all of the factors in high reconnaissance have been considered and a firm plan has been formulated, approach is undertaken. It may vary from normal to steep. Approach should never be any steeper than necessary to clear barriers. During approach, you perform your low reconnaissance. Low reconnaissance starts as soon as you are able to clearly see the landing site. It continues until you are sure that you can land according to your previously made plan. If at any time during the approach you are in doubt that you will land successfully, don't wait to find out. Make a go-around. If high recon has been well executed, low recon should give you no surprises. Touchdown should be smooth and right on the previously planned spot. The next step is ground reconnaissance, and it should be performed as soon as possible after landing. Especially in combat, you must be familiar with the area you are occupying. To make a proper ground reconnaissance, it may be necessary to move around on foot. However, with an aircraft as small as the OH-6, it is usually possible to adequately survey the area and plan ground movement without leaving the cockpit. Movement around obstacles is easier in the OH-6 than in many other rotary wing aircraft. The rotor diameter is only 26 feet 4 inches, and the tail boom and rotor only extends beyond the rotor disc approximately 4 feet. This short extension of the tail rotor beyond the rotor disc makes close quarters turning a fairly safe and simple undertaking. The best technique for moving between two obstacles is to move as close to one of them as you can while observing your rotor tip path. Next, you pivot the helicopter around the tail rotor. The tail rotor does not move its position over the ground, so there is no danger of its hitting an obstacle. If you are going to take off immediately, move the helicopter to the takeoff position as soon as you are assured your ground movement and takeoff plans are adequate. If you are going to remain for more than a few minutes, there could be a wind shift and another takeoff point might be more desirable. Takeoff will vary between normal and maximum performance. In confined area takeoff, a tried and true rule should always be used. It's always better to clear a barrier with a safe margin and a good reserve of power than to clear by a wide margin with no reserve power. Here is another type of advanced flying which will test your skill: pinnacle and ridgeline operation. First, let's define pinnacle and ridgeline. A pinnacle may be a mountain peak with the terrain falling away for thousands of feet on all sides. A pinnacle can also be a small but steep hill. Whatever its height, a pinnacle landing site is a small site where the terrain drops away abruptly on all sides. A ridgeline is an area where the land falls away on one or two sides, such as a bluff, a precipice, or a saddle. Ridgelines and pinnacles present a landing problem, primarily because of the effect which they have on the wind. Wind from any direction must flow up one side and then down the other. On the pinnacle, there is an area of severe turbulence at the upwind edge, where the wind rolls over the top of the slope. At the downwind edge, there is a severe downdraft where the wind falls over the downward slope. All across the pinnacle surface, the wind is turbulent and inconsistent in velocity. On tall mountain pinnacles, the wind blows almost continually, with practically no periods of calm. Winds at these heights frequently have very high velocity. Though lower pinnacles are not so subject to continual high-velocity winds, the wind pattern is just the same. On the hill's pinnacle, there is an updraft on the windward slope, turbulence at the upwind edge, turbulence and inconsistency across the top, and a downdraft at the downwind edge. Obviously, it is important to know the wind direction and velocity in pinnacle operation. The effective wind over a ridgeline will vary with the wind's direction, but when wind is across the ridgeline, the effect is much the same as on a pinnacle. Generally, the effect is not as violent. In pinnacle and ridgeline work, it is important to learn to visualize the pattern formed by the wind so that you can avoid its violent effects. For example, you would not climb to a pinnacle or ridgeline from the downwind side. The downdraft would make flying difficult, if not dangerous. A climb on the upwind side would give you the benefit of the updraft. High reconnaissance should be made with sufficient altitude to avoid the turbulence. After estimating wind velocity, try to form a mental picture of the pattern of eddies, updrafts, and downdrafts the wind is forming in the area. Without these erratic air currents, landing on a pinnacle would be no harder than landing on an airfield. Select a landing site as far as possible from the turbulence at the upwind edge and the downdraft at the downwind edge. Angle of approach depends on existing conditions: the wind velocity, density altitude, gross weight, and availability of forced landing areas. Approach angle may be anywhere from shallow to steep. It should be remembered, however, that a shallow to normal approach provides greater control of the helicopter. On pinnacle landing, low reconnaissance should be very thorough. Don't hesitate to abort it if your landing site is marginal. If the surface is rough or uneven, let the weight of the helicopter down gradually and with caution. An airspeed over altitude takeoff is made since you automatically have adequate altitude as soon as you clear the edge of the pinnacle. Pinnacle and ridgeline operation, as well as confined area operation, are the type work which only a helicopter can do. Your skill will depend on your ability to plan and to control your aircraft in all situations. Maximum performance takeoff and steep approach are two maneuvers which provide an excellent opportunity to improve your ability in the OH-6. In confined areas, remember that each situation presents a new set of problems. The problems can only be dealt with safely by planning each step with care and by being continually ready to pull up and make a go-around. Pinnacle and ridgeline landing calls for an ability to see the wind and to make the wind work for you rather than against you. With its powerful engine and excellent aerodynamics, the OH-6 is capable, provided the aviator at the controls is equally capable. Diligent practice can give you the ability.
Army aviation, like commercial aviation, had its barnstorming days. At considerable personal risk, the aviators proved their point. Helicopters are capable, dependable, and highly maneuverable, but the shows were discontinued. Too dangerous, needless risk. Today, the policy of Army aviation is firm. We know that the OH-6 could far outdo the earlier aircraft in performing hair-raising stunts, but acrobatic flying is outlawed. You must save your daring for the type flying you'll have to do on maneuvers or in combat. But when you don't have to fly between the trees, fly well above them at a safe auto-rotation altitude. Acrobatic maneuvers and unnecessarily dangerous flying are prohibited. In a recent accident report, the cause was stated briefly and clearly. Would you like to face a board with that on your record? Critical flight conditions fall into two categories. There are conditions such as turbulence or over gross weight, where the aircraft is mechanically uncontrollable. And there are situations where the pilot's skill or judgment is faulty. Many skill or judgment accidents occur during hovering. Almost all hovering accidents can be prevented by hovering slowly. This is particularly true in the OH-6. With its clean configuration, it is easy to develop too much speed. Damage caused by hovering is not always to the aircraft. Ground vehicles or personnel can suffer too. Drivers or pedestrians really have no way of knowing where or when you intend to move. When moving at a hover, it is your responsibility to continually check for clearance. Rapid hovering, even in combat or on priority missions, is prohibited. It is a sure sign of an amateurish hot rod pilot. When landing near personnel who may or may not be aware of the danger of tail rotors or drooping main rotors, be particularly cautious and ready to take action if they approach too closely. The placement of cargo in the OH-6 is not as critical as in some aircraft, since the cargo area is directly beneath the main rotor hub. However, CG and cargo weight cannot be ignored. Many in-flight critical situations have been caused by pilots who thought they could carry the same load today that they carried yesterday. The ground elevation may be different, and the density altitude will almost surely be different. When your gross weight density altitude situation isn't obviously safe, don't depend on rule of thumb calculations. Do the written calculating necessary to know what you're doing. If you've done your homework properly with the Dash 10, you'll find it just as easy to calculate as to guesstimate. thorough study and understanding of Chapter 12, weight and balance computation, will teach you how to figure aircraft gross weight easily. Chapter 14, performance data, will tell you how your aircraft will react to a particular gross weight at the existing density altitude. Aviators who enjoy long and pleasant careers always know what they're taking off with and how it will fly before they leave the ground. Many critical flight conditions have been caused by improperly secured cargo. No aircraft can perform safely with a cargo which shifts to the low side each time the aircraft changes attitude. In the Dash 10, you'll find information on the placement and securing of cargo. Though you may have the greatest faith in the ability of your loading personnel, the final responsibility is always yours. To prevent another type critical situation in flight, always check the aircraft for loose items before takeoff. Clothing, tarpaulins, pieces of rope, packing paper, all of them have jammed controls or blown out a door into the tail rotor. Habitually check the cockpit for loose items which might jam the pedals or cyclic. Small, familiar items can easily be overlooked. Even a pencil can interfere with the OH-6 flight controls. If it slipped under this surface, it could easily jam the collective or tail rotor linkage. Such unusual accidents are the ones you can prevent only by constant alertness and attention to details. Another effective way to avoid critical flight conditions is to habitually pause at a hover before takeoff to check instruments and controls. This momentary pause gives you a chance to devote your whole attention to the aircraft's power output and control response. Hover altitude should be 3 to 4 feet, never more than 10 feet. Hovering at excessive height puts an unnecessary strain on the aircraft and can be dangerous in the event of engine failure. And once more, check for clearance by making a clearing turn before takeoff. One advantage of rotary wing aircraft is that you can make a clearing turn easily. Use that advantage to prevent accidents and incidents. Before proceeding with takeoff, we'll examine a height velocity chart for the OH-6. The chart is designed to indicate minimum height above the ground and velocity for a safe auto-rotational landing after engine failure. The curves on these charts are different for various gross weights and density altitudes, but we will show typical curves. The curves divide the chart into 3 areas. The areas might be called safe, caution, and danger conditions. Sometimes the ascending altitude over airspeed curve is called the dead man's curve, but the danger area is not necessarily fatal. Ascents can be made straight up in the OH-6, but pilot technique and control response would have to be excellent if the engine failed. We can also see that a takeoff cannot be made without passing through the caution area. An engine failure would call for quick and proper response. On the height velocity chart, we can visualize why there is only one safest airspeed altitude combination for takeoff. From a takeoff point on the ground, there is only one shortest route to the safe area where an auto rotation is easiest. Any other combination of airspeed and altitude will keep you in the caution area longer. With the high power available in the OH-6, there's a temptation to pull pitch and climb out like an express elevator. The thrill is expensive in fuel, maintenance, and safety. There is also the possibility of a fast airspeed over altitude takeoff. If you must leave the immediate vicinity in a hurry, this is the way to do it. But you'll have your hands full making a safe landing if your engine fails. The short route from the takeoff point to the safe area is the airspeed altitude combination to learn and to use whenever possible. Why risk a critical situation when you don't have to? The proper combination of simultaneous gain in airspeed and altitude will vary with gross weight and density altitude. But under any conditions, the object is to achieve a safe autorotational altitude and airspeed as soon as possible. In all phases of flight, the OH-6, like every other aircraft, has specific operating limitations. These limitations are clearly indicated on the aircraft's instrument panel. The engine instruments are grouped on the panel to simplify monitoring. As on all aircraft, the gauges are marked with green to show the normal operating range. Yellow to indicate the cautionary operating range. And red to indicate the maximums or minimums which should be observed. On all turbine engine aircraft, it is mandatory that the engine instruments be monitored frequently. And overspeed or overtemp can cause complete engine failure. In the Dash 10, Chapter 7, Operating Limitations gives the specific details for every flight situation. You should be completely familiar with this chapter. Each of the paragraphs includes a very important instruction. If these limits are exceeded, record maximum reading on DA Form 2408-13 for maintenance action. These few words must be respected and complied with. Reporting over-limits operation is more than mandatory. It can save your life or the life of anyone who uses the OH-6 after you. Unreported damage can progress to complete failure at any time. It's like leaving a bomb under the seat. Proper reporting and the recording of specific details will assure that action will be taken to be sure there is no hidden damage. When you're responsible for an aircraft engine which develops thousands of RPM and hundreds of degrees of heat, you must monitor often. Trouble isn't frequent, but once started, it can become serious very quickly. In maneuvering the OH-6, you will find that it is a stable and responsive aircraft. The flight controls have good response in maneuvering flight. But because control response is fast and somewhat abrupt, you may have a tendency at first to over-control. Over-controlling, cross-controlling, and poor control coordination can lead to serious difficulties, especially at low altitude. The OH-6 has very clean lines. Its fuselage can move through the air in any direction with low drag. In normal attitudes, this is a real virtue, but in an unusual attitude, resulting from poor control coordination with too little power, the OH-6 will sink very rapidly. This is not a fault in the aircraft. The hazard of high sink rate exists in any helicopter which is flown with poor coordination and inadequate power. There's a case on record where an experienced aviator flying a heavily loaded helicopter carelessly attempted a steeply banked turn at low altitude with insufficient power. The force of gravity exceeded the lift of the tilted rotor disc. He paid heavily for his carelessness. Smoothly coordinated control within the prescribed flight limitations could have prevented this disaster. Slope landing presents another situation where the capability of the aircraft can be exceeded. The cyclic travel of the OH-6 limits the degree of slope on which the aircraft can safely land. Forward cyclic travel is 15 to 17 degrees. Upslope landings are limited to 10-degree slopes due to limited aft support of the skid gear. Rearward cyclic travel limit is 8 to 9 degrees. Downslope landings must be executed with care to avoid damage to the lower vertical stabilizer and tail rotor. Downslope must not exceed 15 degrees. Lateral cyclic travel to the right is limited to 5 1/2 to 7 degrees. Lateral slope landings also must not exceed 15-degree slopes. Lateral cyclic travel to the left is limited to 6 1/2 to 8 degrees. Caution must be exercised on all slope landings. Much of the OH-6's ability to operate on sloping terrain is derived from the landing gear struts. Caution should be used when centering the cyclic, because this extends the upslope strut and increases the tilt of the aircraft. In fine weather, flying the OH-6 is quite simple. Although it is not equipped for instrument flight, most weather problem areas can be overcome, provided common sense and prescribed flight limitations are observed. Let's run through the list of common weather hazards. All of them are familiar to experienced aviators. Moderate precipitation, a gentle rain or snow, has no effect other than to reduce visibility. Flight altitude should be sufficiently above the terrain to avoid obstacles, but low enough to maintain positive visual contact with the ground. The OH-6 is not equipped for IFR operation. In very heavy precipitation, flight should be postponed until safe takeoff and landing are assured. Precipitation makes flight more difficult. It only prevents flight when it is excessively heavy. Fog and smog present much the same hindrance to flight. Care must be taken to maintain visual contact. A low ceiling condition must also be dealt with cautiously. Flying beneath the overcast involves the danger of having the ceiling descend to a very low level. The only acceptable procedure is a prompt 180 to avoid the no visibility area. Flying VFR on top of a heavy overcast requires that you be certain that your destination will be in the clear when you arrive. Don't accept a needless risk by gambling on a stale or questionable forecast. Low ceilings in some geographic areas are common. If the ceiling is forecast at 500 feet, it may remain at 500 or it may descend. Don't depend on ceilings to remain stable. With a clear sky, the horizon is visible. Altitude and attitude perception is not particularly interfered with. But when the sky is heavily overcast, the horizon disappears completely. Ability to judge altitude above the surface or even flight attitude becomes a serious problem. Dependence on instruments is essential. Don't trust your senses. Dust can also cause complete loss of visual reference. Landings must be made without hovering. Dust or snow will blow up and obscure the horizon. But a safe landing can be made if it is made directly to the ground. Whiteout is a particular hazard in the Arctic, but it can occur on any level snow-covered terrain, over water, or on a landing area covered with powdery snow or dust. Engine icing in cold weather is a potential hazard in the OH-6. As with any turbine engine aircraft, the turbine outlet temperature must be monitored for a gradual increase above normal when icing is possible. Moving the engine de-icer lever to the rear will direct hot exhaust air into the compressor inlet to prevent icing. Remember that icing can occur on cloudless days if the temperature and humidity are right. Hot weather has several effects which can lead to a critical condition. One of them is greatly increased density altitude. If you're operating from an airfield at 1,000 feet on a standard day, the density altitude will be 1,000 feet. But with the temperature in the high 90s, the density altitude will be almost 3,500. That much additional altitude can lead to a critical situation if you're operating close to maximum gross weight. In very hot weather, engine performance can be temperature limited. You have to fly by your TOT gauge as much as your torque gauge. Hot weather in a usually temperate area calls for caution. You can't operate just as though the weather was normal. Turbulence can mean the mild bumping caused by thermal air currents. Or it can mean the uncontrollable violence of a thunderstorm. Perhaps you've seen the instruction manual on how to fly through thunderstorms. It's a very brief pamphlet. Just one word. That's all you need to know. Ask any flyer who has penetrated a thunderstorm and lived. Even in light turbulence, you must fly at reduced airspeed. Keep your RPM up to provide good control response. If control response becomes marginal, don't fight it. Land and wait out the weather. You'll get there later, but alive. The OH-6 can take mild turbulence in its stride, but no light aircraft should be intentionally flown into moderate to severe turbulence. All the common weather hazards increase your chances of getting into a critical flight condition. Be more alert when the weather is foul. Army helicopters have been vastly improved, but the situations which lead to critical flight conditions remain essentially the same. Acrobatics and unnecessarily dangerous flying are no safer in an OH-6 than in any aircraft. Hovering accidents are common. They can almost all be prevented by hovering slowly. Cargo loading, its placement, gross weight, and security are your responsibility. No aircraft can perform safely with a shifting cargo. Habitually pause at a hover before takeoff. It's much better to discover trouble at a hover than in a climb. Study the OH-6 height velocity chart. With it, you can determine the short route to safe height and airspeed. Become thoroughly familiar with the operating limitations of your aircraft, and don't underestimate the importance of reporting over speeds, over temps, and hard landings. The OH-6 controls provide smooth response when properly handled. But over-controlling, cross-controlling, or inadequate power are just as dangerous as in any helicopter. You can't do anything about changing the weather, but you can learn when to fly and when not to fly. The basic rule for avoiding critical flight conditions is simple. Fly by the book. Follow all recommended procedures no matter how much experience you gain or how familiar you become with the aircraft. Learn the rules about height and velocity, calculating gross weight, handling the aircraft in foul weather. Learn all the rules and adhere to them each time you fly. The OH-6 gives you plenty of warning when the engine quits. A change in engine sound may be detected first, but a decrease in torque and RPM may be the first change noted. When N1 falls to 55%, the engine out warning light flashes, and a beeping tone is heard in your headset. Engine failure without warning is a rare occurrence. When it does occur, immediate establishment of an auto rotation is standard procedure. An engine restart should only be attempted if you have adequate altitude and you are sure you can restart the engine. In this film, we will learn about auto rotation and other emergency procedures in the OH-6. In training, you will practice basic auto rotations heading into the wind from a specified standard altitude at an entry airspeed of 100 knots. With an actual engine failure, these conditions may not exist. We will see how other situations are handled later. Auto rotation is entered by reducing collective pitch and simultaneously rolling off power to the flight idle detent. As power is reduced, heading is stabilized by trimming the pedals, and a deceleration to 60 knots is achieved by applying aft cyclic control pressure. Rotor RPM and N1 readings must stay within acceptable limits. Throughout the descent, monitor the rotor RPM and gas producer frequently. Maintain 60 knots to an altitude of 50 to 75 feet. Then start to decelerate by applying additional aft cyclic pressure. Pressure must be applied properly. Too abrupt a movement will cause the OH-6 to climb. Too slow a movement may fail to reduce rate of descent. Gradually increase aft cyclic pressure to further reduce airspeed. When the aircraft is 10 to 15 feet from the ground, apply sufficient collective pitch to slow the rate of descent. Near the ground, apply additional collective pitch to cushion your landing. Maintain heading with the pedals. In addition to basic auto rotation, you will practice 180-degree and precision auto rotations. This training will prepare you to handle an engine failure in any flight situation. Engine failure can occur at a hover, during climb out, at low altitude and high speed, or during normal flight. Dealing with engine failure at a hover is quite simple. The principal thing to remember is not to increase or decrease pitch. Leave pitch at the setting used for hovering as you apply right pedal to compensate for rapidly decreasing torque. Prevent drift over the ground with cyclic control adjustments. The aircraft will settle as rotor RPM decreases. Just before contacting the ground, apply sufficient collective pitch to cushion your landing. The key factor in dealing with engine failure at a hover is to recognize the power loss quickly. Do not attempt to maintain the hover by increasing collective pitch. Conserve rotor RPM and allow the helicopter to settle. When engine failure occurs during climb out, the same general principle is used. The first indication will be a sensation of loss of power. Reduce collective pitch to conserve rotor RPM. The amount of pitch reduction depends on your altitude. Apply aft cyclic pressure to decrease forward speed. As you reduce speed, the aircraft will descend. Close to the ground, level the aircraft and apply collective pitch to slow descent. Just before touchdown, use the remaining pitch to cushion your landing. With engine failure during climb out, a hard landing or collision cannot always be avoided. If possible, shoulder harness should be locked and switches off before ground contact. The OH-6 has excellent characteristics for landing after low-altitude, high-airspeed engine failure. Its low drag and rotor system design permit a power-off climb to an altitude from which a normal auto-rotation can be made. Again, the important factor is skillful rotor RPM management. When power is lost, a speed reduction climb is started by applying aft cyclic. During the climb, collective pitch should be gradually reduced so that pitch is full down when the climb is terminated at 60 knots. Care must be taken not to permit rotor RPM to exceed limits during or following the climb. Sufficient altitude will be gained in the climb to permit a normal auto rotation with a fairly wide choice of landing sites. At low altitude and high airspeed, with a favorable wind and weight, it is feasible to climb 200 to 300 feet after engine failure. With engine failure during normal flight, an autorotative descent and landing is made. The fuel valve should be pulled and all electrical switches off, except when the landing light will be needed. In autorotation, the gliding distance and rate of descent of the OH-6 is very favorable when compared to other present-day helicopters. Despite this excellent capability, it is not always possible to land in an ideal area. Two less desirable alternatives are possible: landing in trees and ditching in water. A tree landing, properly executed, is not excessively hazardous to personnel. The principal requirement is cool and capable management of the descent. Choose carefully and select an area where the trees are fewer and smaller. At treetop level, zero your ground speed and permit the helicopter to settle. With capable handling, you can settle between trees rather than in a tree. Just before the rotors contact the trees, use full collective pitch to attain minimum rate of descent and slow blade rotation. Many tree landings have been walked away from with little or no injury to crew or passengers. When landing in trees, as with any emergency landing, shoulder harness should be locked and fuel valve and all switches off. In flight over large bodies of water, ditching may be unavoidable. However, every effort should be made to reach land, since even a perfect ditching is dangerous. Ditching may be necessary with power in the event of an uncontrollable fire or other damage. Ditching may also be performed without power after engine or powertrain failure. In ditching with power, the OH-6 is brought to a hover close to the water, and all passengers and the co-pilot jump from the aircraft. You next move the aircraft well away from the personnel in the water. If the co-pilot's door is unlatched, it should be firmly secured to provide as much flotation as possible. After the battery and generator switches are turned off, lock your shoulder harness, then jettison the pilot's door. With your escape route ready, cut off the engine by turning the twist grip to the fully closed fuel cutoff position. As the engine dies, increase pitch to maintain the aircraft just above the water. With pitch full up, the rotors will decelerate and the OH-6 will settle into the water. As water contact is made, bottom the pitch. This is very important. If the blades are not at minimum pitch, they will skip off the water as the aircraft is rolled to the left. Left cyclic is applied to dip the blade tips into the water. With minimum pitch, they dig in and stop without skipping. As soon as blade rotation is stopped, climb out and move away from the aircraft as rapidly as possible. The aircraft will sink quickly, and there will be considerable steam and noise as the hot engine contacts the water. We can readily see why ditching without power is executed in exactly the same way, except that an autorotation terminating at zero ground speed is made to hover altitude. All personnel, crew, and passengers must remain strapped in until blade rotation is stopped. Fortunately, the exceptional autorotative glide range of the OH-6 makes ditching a rare necessity. Tail rotor failure is not an occurrence either, but you should know how to deal with it. There are two forces which prevent main rotor torque from rotating the fuselage of a single rotor helicopter. One is the counteracting force of the tail rotor. The other is the streamlining effect of the relative wind passing over the fuselage. For streamlining to be effective, the power setting which induces torque in the rotor plane and the airspeed must balance. If the airspeed is sufficient and the power setting is not too great, the fuselage will not rotate, even though the tail rotor is ineffective. This balance between airspeed and power setting is the key to managing tail rotor failure in flight. You may not even be aware of tail rotor failure immediately. The first indication may be a lack of response to pedal movement. The pedals will be completely ineffective. The aircraft may yaw to the right, but flight can usually be maintained as long as torque and airspeed are kept in balance to prevent excessive yaw. When powered flight cannot be maintained, auto-rotate immediately to a suitable site, preferably upwind. As soon as you reduce power to flight idle, yawing will decrease greatly. Normally, however, you can continue powered flight to a suitable landing field. When you reach the landing area, make a full auto-rotation landing into the wind. Maintain 60 knots indicated airspeed and keep turns to a minimum. On a level surface, make a running landing into the wind with a touchdown airspeed adequate to keep the yaw at a minimum. With tail rotor failure at a hover, you will not only lose the torque counteracting effect of the tail rotor, but you will have little, if any, relative wind and no airspeed to prevent rotation of the fuselage. Tail rotor failure will cause a sudden yaw to the right, which, if allowed to continue, will cause rotation or spinning of the aircraft. Act immediately by turning the twist grip to flight idle and make a hovering auto-rotation. Since the fuselage may continue to rotate slowly to the right, use collective pitch carefully to cushion your touchdown as much as possible. Damage and injury can be avoided by expert control manipulation, even though the tail rotor controls are completely ineffective. So far, we have only discussed tail rotor failure. Tail rotor control malfunction is also possible. In a control malfunction, the tail rotor continues to deliver thrust, but the degree of thrust cannot be controlled due to a break or jamming in the tail rotor control system. Normally, when this occurs, the pitch setting at the moment of malfunction will remain fixed in the tail rotor. Thus, there are three possible tail rotor fixed pitch conditions. If control malfunction occurs in a high power situation, as in takeoff, the blades will be fixed near full pitch position. In a low power situation, such as approach, the blades will be fixed near minimum pitch. At a normal cruise power setting, the blades will be fixed at an intermediate degree of thrust. Since tail rotor control malfunction has so many variables, we can't give specific solutions. In general, however, with failure at full pitch, difficulty will be noted only when power is reduced. Therefore, do not auto-rotate. Proceed to an airfield and make a powered landing. Incidentally, with a full pitch malfunction, the OH-6 will yaw to the left when power is reduced. At minimum pitch, with a tail rotor control malfunction, do not increase power. This would cause a severe yaw to the right. The best solution is to auto-rotate immediately. With a malfunction at normal cruise and the tail rotor at intermediate pitch, the aircraft's reaction will be similar to a full pitch malfunction, but not as critical. It is probably best not to auto-rotate. Maintain airspeed to reduce yaw and make a powered landing. Some side slip should be expected when power is added during landing. Tail rotor control malfunction is a serious emergency. It calls for ability to immediately analyze the situation, to take appropriate action quickly and calmly. Fire is also an emergency which calls for a calm attitude. It is a rare occurrence in well-maintained and inspected aircraft. The most common type of fire is engine fire during starting. A malfunction may cause raw liquid fuel to accumulate in the combustion chamber. Normally, such fuel should escape through a drain provided in the bottom of the chamber. If the engine is hot, this fuel may ignite, or it may ignite when normal ignition takes place. No serious damage will occur provided proper corrective action is taken promptly. Immediately roll the twist grip to the fuel cutoff position and continue to motor the engine with the starter button. At the same time, pull the fuel valve to closed. As soon as all of the liquid fuel is consumed, the fire will go out. Another starting attempt should not be made until the cause of the malfunction is determined and corrected. It is also possible for engine fire to occur in flight. This might be considered a special type of engine failure, and the same procedure is used. If power remains available, powered flight may be used for 2 or 3 minutes to reach a suitable emergency landing site. Fuselage fire and electrical fire may also occur, and the procedures used are those used in any aircraft. With a fuselage or cargo fire, use the fire extinguisher, and if the situation is serious, land immediately. With electrical fire, check the instruments to attempt to locate the faulty circuit. Then pull the appropriate circuit breakers. Snap off the battery and generator switches, and land as soon as practical. To clear smoke and fumes from the aircraft, open the rear air ventilator and rear cabin doors. The fuel system and electrical system of the OH-6 differ little from other turbine helicopter systems. Manual fuel control can be used to override a malfunctioning fuel control unit, and with the generator out, flight should be continued only if absolutely necessary. Two special problems which can occur in the OH-6 are cyclic one-way lock failure and runaway cyclic trim actuator. These malfunctions can be dealt with easily. The cyclic system one-way lock, which prevents rotor force from causing aft motion of the cyclic control stick, is dependent on a check valve for proper operation. If the check valve fails, stiffness in aft movement will be noted. A pull of approximately 30 pounds will clear the lock and relieve the stiffness. It isn't necessary or advisable to clear the lock in one pull. The maneuver this would cause might be dangerous. Overcome the lock only sufficiently to safely fly the aircraft. It is possible for either of the cyclic trim actuators to develop a switch failure or short circuit. This would cause excessive and unwanted trim force, either fore or aft or to one side. The cyclic trim circuit breaker should be pulled to stop any further movement of the defective actuator. Flight may be continued by simply increasing the force applied to the control stick to override the out-of-balance trim condition. The aircraft can be flown with a defective one-way lock or trim actuator. Flight need not be terminated. Now let's review what we have learned about emergency procedures. Auto-rotation in the OH-6 calls for no new or unusual procedures. The aircraft has an excellent glide range and minimum rate of auto-rotative descent. Engine failure at a hover, during climb out, at low altitude and high speed, or during normal flight, all call for conserving of rotor RPM. Landing in trees and ditching are both last resort actions. If landing in trees is necessary, carefully select an area where the trees are smallest and furthest apart. Just above the trees, zero your ground speed and settle in between trees rather than in a tree. Ditching should be accomplished only when it is absolutely impossible to reach land. In ditching, control of the aircraft must be retained so that the rotors can be stopped before the fuselage submerges. Personnel that do not jump before water contact must not leave the aircraft before the rotors have stopped. Tail rotor failure and malfunction can be dealt with, provided the situation is properly analyzed and action is taken quickly and calmly. Fire in any aircraft is exceedingly dangerous. Quick recognition of the type of fire and rapid, proper response are imperative. With cyclic system one-way lock failure, the lock can be overcome by exerting aft force sufficiently to safely fly the aircraft. With a runaway cyclic trim actuator, the circuit breaker should be pulled and flight continued, using sufficient force to overcome the out-of-balance trim condition. The OH-6, because of its ruggedness and simplicity of design, is not an emergency-prone aircraft. But this does not mean that it will never fail. Prepare yourself for emergencies so that if one occurs, you can handle it with calmness, confidence, and capability.
Vicinity of phase line red, encountering dense fog, executing a 180 in order to...
As the pilot was trying to make a 180-degree turn out of the fog, his aircraft struck the tops of some large trees which lined the banks of the river. Was this fatal accident avoidable? What would you have done to get out of this situation? A UH-1 with a crew of 3 and 2 passengers took off with a forecast low ceiling and with what they believed to be sufficient clearance to allow safe flight along their planned route. Later, the sole survivor of the crash told investigators that while flying through one of the mountain passes along their route, they encountered fog or low-lying clouds. The next thing he remembered was being evacuated from the wreckage. Apparently, the pilot, in his attempt to return to visual meteorological conditions, flew into the side of the pass. The wreckage was located several hundred feet up the side of the mountain.
I'm Bill Delton, an air safety specialist at the United States Army Agency for Aviation Safety. I've just been getting some current weather information. Weather is an interesting subject for almost everyone. But for those of us in aviation, weather is a matter of vital concern. The cause of mishaps such as you've just seen is often labeled unintentional flight into instrument meteorological conditions, better known as inadvertent IMC. These inadvertent IMC mishaps should be of great concern to the aviator and to the aviation commander because they are so devastating. Come to the office with me and let's discuss this problem further. IMC mishaps seldom result in only a broken skid or bent wing. They are almost always catastrophic in terms of lives lost or equipment destroyed. These occurrences seemingly defy all logic, and apparently they do not discriminate between the inexperienced and the experienced aviator. One of the most common causes of inadvertent IMC accidents is pilots attempting to maintain visual meteorological conditions, VMC, in marginal weather. Why do they attempt to fly visually under these conditions when they would quickly pull over and stop if they encountered the same conditions while driving a car? Suppose on my way to the office, I encountered fog. Would you attempt to fly VFR with this kind of restricted vision? Many aviators have. Maybe that's an exaggerated situation, but don't you think it's appropriate? Come on inside. In one recent 12-month period, 12 of the 94 accidents recorded involved weather. These 12 weather accidents accounted for more than half of the 55 fatalities for that period. How can an aircraft be clear, blue, and 22 at one moment, and inadvertently IMC the next? Obviously, aviators and commanders are neglecting some key element in VFR procedures. What is this elusive element? It's far more than just apprising aviators and commanders of the inadvertent IMC problem. Too often, the position is taken that there is no such thing as inadvertent IMC, and much like an ostrich, we've covered our heads and hoped the problem would go away. Rather than do this, we must first recognize that we have a problem and then go about finding a means of solving it. Unintentional flight into instrument meteorological conditions has long been a problem for Army aviation. Terrain flying techniques will enhance the survivability of Army aircraft on the battlefield of tomorrow. However, our techniques for dealing with inadvertent IMC at terrain flight level have not proven to be fully adequate. For example, one of our main villains, fog, is a common and persistent weather hazard encountered in aviation. Once it was primarily a hazard only during takeoff and landing, but terrain flying techniques have brought aviation down to these altitudes on a regular basis. When planning for such a mission, you should pay particular attention to your weather briefing, especially the current and forecast temperature and dew point. When these two get to within a couple of degrees of each other, some type of fog will develop. Add dust particles to this, and you have all the makings of dense fog, which will be around for some time. Some areas, such as large bodies of water, swampy or marshy land, heavy forests after rain, and valleys, are more apt to become unexpectedly foggy than others. Although FM 1-1 terrain flying presents a new approach to the inadvertent IMC problem, we find that many unit SOPs still contain the old cure-all of execute a 180-degree turn. Successful transition from visual meteorological conditions requires the logical application of a step-by-step procedure to avoid loss of control, confusion, and more importantly, a catastrophic mishap. Analysis of aircraft accident experience has identified task errors that occur repeatedly in inadvertent IMC mishaps. Identification of these task errors led to the development of an inadvertent IMC procedure, which has been labeled the 5 C's. They are control. When you inadvertently encounter IMC, immediately shift your attention to your flight instruments. Level your aircraft while maintaining desired heading. Adjust power to establish a positive rate of climb and stabilize airspeed. Coordination. Establish beforehand that the pilot at the controls will concentrate primarily on his flight instruments. The co-pilot is to monitor the flight instruments as well as the engine instruments and advise when visual conditions are again encountered. Clearance. Ensure clearance above the highest obstacle. Gain required altitude with a straight controlled climb. And then, if required, select and turn to appropriate course heading. Call. Make required radio calls for necessary assistance. Inadvertent IMC can be a killer. This single factor is cited as a cause in more fatal aircraft accidents than all other cause factors combined. As opposed to deliberate instrument flight, inadvertent IMC is an unplanned event generally occurring at low altitudes and low airspeeds and with the aircrew totally unprepared for instrument flight. Aircraft impact angles and speeds, as well as statements of witnesses and survivors, support the contention that a pilot generally makes no attempt to transition to instruments when suddenly losing ground reference. Instead, he tries to return to VMC, either by executing a turn or by descending. In any event, he is attempting to exercise an option which at that time does not exist. Turns away from bad weather or unscheduled landings are to be made before IMC is actually encountered. Once ground reference is lost, the pilot must make an immediate and complete transition to instrument flight. It goes without saying that in a situation such as inadvertent IMC, some of these instruments are not as important to aircraft control as others. The suddenness of inadvertent IMC will not allow the aviator to establish a complete scan. A pilot must learn to cross-check the most critical instruments first. Step by step, he must use the attitude indicator to level the aircraft, then the heading indicator to maintain selected heading. Once established, by reference to the torque meter, he now adjusts to climb power. And finally, the airspeed indicator to make certain he is established in forward flight with airspeed stabilized. This procedure describes the first C in our recipe, control. The second C, coordination, is taken care of at some time before the flight. It must be established beforehand that the pilot at the controls will concentrate primarily on flying the aircraft on instruments. The co-pilot will monitor the instruments and advise when visual conditions are again encountered. Clearance. Make sure you have adequate clearance above the highest obstacle. This is also covered in the step-by-step procedure when a straight controlled climb is established. Another recipe ingredient, course, is included in the procedure when you make certain you are maintaining the correct heading. The final C, call, is accomplished only when the immediate action steps have been successfully completed and you're ready to begin executing your established inadvertent IMC recovery plan. As a minimum, the 5C procedure, which evolved from combined research and operational experience, should definitely be included in your unit training program. The time to plan for an encounter with inadvertent IMC is before, not during the encounter. The 5C procedure is easy to remember and could be well worth the time it takes to do so. Think about it.